say que compute the curve. So one vector field is given. Question 2. One vector field is given. By the way, this vector field is in 2 dimensions, not in 3 dimensions, because we have PQ, no PQR. Okay. And verify if it is conservative and try to find the potential function. Well, it's easy. The formula for, so the first thing you should do to verify if conservative or no, you compute the curve of the vector field. The formula 2D is super easy. Is partial derivative q with respect to x minus partial derivative p with respect to y. It's doing partial derivative q with respect to x and y minus partial derivative p with respect to y is 2y. The answer is minus y. And minus y is not 0. Si it's not 0, the statement is clear. No conservative, no potential. So the no conservative therefore potential functions do not exist. End the story. Any question? No? Everything okay? Chewy, what the hell? Okay, no problem. Yes, Alejandro is a yes. Okay, let's move on to number 3. Number 3 is similar. Is the we have a vector field again. This vector field is sine x plus y, comma, sine x plus y. Okay, the functions are the same. This is P, this is Q. Same formula, same procedure. Compute the curve of this vector field is qx minus py. So partial derivative q is this guy with respect to x is derivative sine cosine x plus y. Multiplication by the chain rule, no, the derivative of the argument, but also because the derivative of the argument is 1. The derivative x with respect to x is 1, and the derivative y with respect to x is 0. And the derivative partial derivative minus partial derivative p with respect to y, this is p now, it's exactly the same. It's cosine xy x plus y, sorry, times 1. It's identical. The answer is 0. Cool. Therefore, a conservative field vector field and the potential function exists. I want to find right now. How you find? You compute the anti-gradient. So you take component by component P and Q and integrate. For example, the formula is the potential function is equal to the antiderivative of antiderivative of P dx. Okay, and also the potential function is the antiderivative q with respect to y. It's doing. So it's antiderivative sine x plus y dx And it's obvious que antiderivative sign is minus cosine x plus y. And you put a constant or arbitrary function, but it's not important. This is irrelevant because you complementary this answer and this answer together without repetition, and that's it. And the second is antiderivative sign x plus y dy. In that case, is again is minus cosine x plus y, and that's it. Now, in this case, they are perfect coincidence. Cool, no problema. I understand. And you take both. Both no. You take only one because it's repeated. So the potential function is minus cosine x plus y. Boom. Final answer. Any question? Okay, in few words, the thing we are doing to compute the potential function is compute the anti-gradient. The anti-gradient is the antiderivative component by component. Suppose we have three components, PQR, so you compute the antiderivative P with respect to X, Q with respect to Y, and R with respect to Z. And finally, we collecting every answer.
Professor?
Okay. Go ahead.
So it's you don't add them. You just choose one.
No. You collecting. See, they are repetition. You take one time.
Okay.
Okay.
And if they're not the same, you said you add.
No. You take one.
Oh, you take one.
You take one.
Okay.
You have Maria, and Juana. When you take one Maria and Juana. In this case, no, because it's Maria. You take only one time. So it's union, put together without repetition.
Okay. So if there was another different one, you would put below that. Would you say would you put like a little subscript like 1 under it, or like or little subscript 2 after it, and then say equals?
I don't understand very well what you think you try to explain me, bro.
Well, if you put a subscript after the phi,
subscribe after the phi,
like the little number below, like like when you put the 0 below, like to symbolize the not.
Yeah.
Is that how you would write it, like for notation?
I don't understand very well the thing you try to explain.
Well, if there was another potential function, how would you write it? Could
you see in the example 4, in the question 4, you see. Okay. Question 4 is the same. Compute the curve of the vector field. In this case, the vector field is 3-dimensional. The vector field is y e to the x, comma, e to the x plus 1, comma, e to the z. Okay, the question is similar. Verify if it's conservative or no, and try to find the potential function. So always is the same. You compute the curve. The curve in 3D is a vector. So the curve in 3D, the formula is, so the curve of this vector field is the dot product, the cross product, sorry, nabla F. And remember nabla. Nabla is, this is IJK, the classical orthonormal univectors, and nabla is partial derivative with respect to x, is totally symbolic. Partial derivative with respect to y, partial derivative with respect to z. And you copy here PQR. P is this, Q is this, R is that. Basically is y e to the x plus 1 and e to the z. Boom. And now we compute the determinant. That's all we are doing. I propose this organization. You copy I here and do the decay, put the parenthesis because I know that you have two guys, one positive, one negative, huh? And you delete mentally this and this. Partial derivative of this function with respect to y is obvious. It's zero, no? Because do not depending of y, and this do not depending of zero. 0 minus 0. So at least this component is 0. Minus j, two parentheses, you delete mentally this and this, and you dedicate this and this. Partial derivative with respect to x is 0 again. Partial derivative with respect to z is 0 again because do not depend on z. Blockade, two parentheses, and you delete this and this, and you dedicate your time doing this partial derivatives. A partial derivative with respect to the x is just e to the x, no? It's the same function, no? Because partial derivative 1 is 0, and partial derivative with respect to y is e to the x, and this is minus. Again, it's 0, any component, because this is equal to 0, is 0. It's 0, those are 0, 0, 0, therefore the curve is the curve of this vector field is the 0 vector. Okay, it's equivalent to 0, 0, 0. So we can affirm that it is conservative. Okay, after that, we dedicate the time, compute the potential function, because I know it exists. So remember, anti-derivative, component by component, que es equivalent to say anti-gradient. So the function phi x, y, z, three variable, three dimension, is the antiderivative of the y e to the x dx. But it's also antiderivative e to the x plus 1 dy is also antiderivative, the last component is EC, no? DC. Is it okay? Yeah. Now let's do it. This is easy because y is a constant, you put outside the antiderivative, and antiderivative e to the x is e to the x, so the answer is y e to the x. Here, it's different because antiderivative e to the x with respect to y is e to the xy, no? Plus antiderivative 1 is y. And this is e to the c. End the story. So what is my potential function? Phi x, y, z, one of the collection of this element. By coincidence, this and this is the same. You take one time. This is y e to the x plus y also I taking plus e to the c. End the story. Do you see more clear now?
Yes. Just
easy. Easy. Everyone follow me so far? 100 points so far in the test?
Yes, following.
Excellent. Can you raise the bar or no?
1 second.
No, it's okay. We have time to do perfectly. Okay? So any minimum doubt, any minimum question, don't hesitate to ask me. I know that something is complicated, but no. Only no. Okay. Erase? Yes or no?
Yes.
Okay, number 5. Let's compute. Compute. Evaluate. Using fundamental theorem of calculus of the line integral. This line integral. Okay, the information that's given is 0,02, so 2 points. See, the line integral, we have no information. About the curve. Normally, when you have line integral, is mandatory the function, this is ds, pero little s, no capital. It's mandatory the curve, but in this case don't give the curve. I suppose que is because the vector field is conservative. And so now we compute, you see, when the vector field is conservative, the circulation integral do not depend of the path. We depending only of the initial starting point and ending point. Okay, it's given. This is P1 and P2. Okay, so the first thing you should do is, proof to make sure we are doing well. Proof that the vector field is conservative. Yeah, and also determine the potential function and evaluate the potential function. And between the point, entonces, potential function evaluate in P2 minus potential function evaluate in P1. You compute the answer of this integral. Okay. However, I don't know. I don't like this format. I don't like this format of this. I take this for the one study guide in internet. But you can write this integral. So at least the integrand part, including the differential part. You can, for example, write like that: x plus y plus c dx plus x plus y plus c dy plus x plus y plus c dc. Okay, because you distribute it here. Either way, you can distribute it here, you obtain 9 term. But no, because what is my goal? My goal is now apply the idea, basic idea of the dot product. So now my vector field, okay, always is PQR, no? PQR multiplication dot product dr, and dr is a vector dx, dy, dc, ¿no? Entonces es obvio que this is P, this is Q, and this is R. And the answer of this is dot product F vector dot dr. Okay, this is, I put intentionally this example because sometimes in the book and the study guide, it's written the line integral in different weird. So you take always systematically to this way, line integral and the curve C of f dot dr, and you don't understand very well the relationship between this and this. You see or no? You see? So how you find the vector field, no? Okay, is coming this line integral. You follow me?
Yes, we're following.
What should I do in your opinion now? Remember our goal. Our goal is compute this line integral that represents circulation in between 2 points. Okay, so now I need to verification since this vector field is conservative or not. And determine the potential function. Similar. So now the curve of this vector field is I, J, K. The nabla operator the component of the vector field, in this case, is the same. X plus Y plus Z. X plus Y plus Z. X plus Y plus Z. Okay, ready. Okay, now remember the organization. Okay, I propose you always I minus J and K. And 3 parentheses. Inside the 3 parentheses, we have 2 quantity, one is plus and one is negative. In this case, I is partial derivative with respect the y is obvious que 1, no? And partial derivative with respect to z is obvious as well. And similar situation happen in the rest. This is this partial derivative with respect to x1 minus 1. And finally, partial derivative this is with respect to x1 minus 1. Again, is 0 component I, 0 component j, and 0 component k. And the vector is 0, 0, 0. The curve is 0. It's null vector. No equal to 0, it's null vector. This is null vector. It's conservative, and we are ready to start the potential function. Okay? And the potential function, you computed 3 antiderivatives. Actually, it's the same PQR. It's a coincidence in this problem. Not always happen, but okay. The answer is we integrate with respect to x is obvious. Okay, the answer is x squared over 2 plus xy plus xz. When you integrate with respect to y, here we have xy, we have y squared over 2, and we have cy. And when you integrate with respect to z, we have xz plus yz plus c squared over 2. So what is my potential function? Phi x comma y comma z. Yes, you take the collection. Look, identification here, the quadratic. I copy. To sound elegant, the answer, I copy the quadratic first. X squared over 2 plus y squared over 2 plus c squared over 2. And now we copy no quadratic, linear. To see we have xy, repeat it here, take one time. xc, repeat it here, take one time. xc, and this, cy. Boom. And this is my potential function. And the rest is magic, because you compute the integral without do any integral. But actually, we did the gradient, anti-gradient, and this potential function allow me to compute the integral. So you evaluate the potential function and the point is given in 1, 1, 1, 1 minus 0, 0, 0. That's obvious. When you plug it in 0, the answer is 0. So that part is 0. It's obvious. But that part, no. That part is 1/2 plus 1/2 plus 1/2 plus 1 plus 1 and plus 1. And the answer is 9 or 2. Boom. Any question? What part is confusing? Easy or no?
Yeah, it's easy.
And number 6 question is similar. Okay. Let me erase. Sixth question is simple. Is compute or evaluate whatever the integral from the point 0, 0, and 0 and 1, 1, 1. When you see the point and no curve, it's because the vector field is conservative. Entonces x dy plus y dx plus z dz. Okay, entonces now I suppose that this integral comes from, for the dot product, one hypothetical vector field that dr. Entonces this hypothetical vector field have the component PQR multiplication by the arc is dx, comma dy, comma dz. When you are doing the dot product, it's obvious, no? Okay, we have line integral p dx plus q dy and r dz. So try to compare this equation and this integral and this integral, no? It's obvious okay, who is p, who is r, and who is q. This is p because it's, you know, beside the x, no? And this is q, and this is r. So we discover okay, our vector field is the vector field y, x, z. Entonces I need to investigate if this vector field is conservative. I smell. I suppose that this is okay. It's conservative because now give me the curve of the perform the line integral. And see I have a curve, so I need the parametrization of the curve and try to change the line integral to the single cal1 integral. In this case, no. So now you smell that this vector field is conservative. Now, but I try to prove using the curve. The curve of the vector field and this notation que es nabla cross product f. Remember, nabla operator is I, j, k, the symbolic operator, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. And you copy here PQR. But in our example, P is y, Q is x, and R is z. Okay, one more time. You separate this I to parenthesis minus j two parentheses, one parenthesis, open, close, and k, one parenthesis. And now let's do this. Partial derivative this with respect to y is 0, partial derivative this with respect to the z is 0, 0 minus 0. Here, here. Partial derivative this guy with respect to the x is 0, not depending of x, not depending of y. And finally, this and this, that part, this depending, yes, this depending of 1. Partial the x with respect to x is 1, and partial the y 1. 1 minus 1 is 0. 3 components are 0. Now the curve is equal to 0 vector. Now a conservative, and you can find the potential function. Potential function and 3 variables, x, y, z is the collection of the antiderivative component by component, and this antiderivative together is the anti-gradient. Okay, so now you integration p dx, integration q dy, integration r dz. Who is p? P is y, y dx. Es obvio que the answer is xy. Because y is a constant, I put outside, integral dx is just x. And the second is q is x, no? X dy. Always the same. You see that sometimes it's repeated expression. And finally is r, but r is c, no? Integral c dz. Oh, this is different. This is c squared divided by 2. Therefore, my potential function x, y, z is, you take this one time xy plus c squared over 2. My potential function, you see this is repeated. You take one time only, and this is completely different. Now my goal is to evaluate the potential function in 1, 1, 1, minus is 0, 0, 0. 0, 0, 0 again is 0. Because normally this is like a polynomial. And 1, no. And 1 is 1 times 1 plus 1 squared is 1/2, 3/2. Boom, final answer. This is the answer of the circulation line integral without doing any integral. Only another method is discover si the vector field associated with this integral is conservative or not, and find the potential function. Okay, cool. Everyone follow me? I don't know exactly what happened with this whiteboard. Okay, I need to reload anytime. Maybe I switch into another. Let me see. Another. Okay. Do you see the whiteboard, right? Yes. Okay. Now number 7. Number 7, yeah, change completely the problem. Now evaluate using Green theorem. Okay, you have one line integral in the closed curve, y squared dx plus x squared dy. And the curve is given, of course. The curve is a semicircle. Let me try. We start here at -1, +1, and 1 here. This is the curve. In that direction, in that direction. This is my curve C. This is X, and this is Y. Okay. So I can see clear. So you write in the other format of the vector field, no? I discovered that this line integral and the closed curve is f double dr, and the old format is well, the vector field is pq, no? Because it's in two-dimensional, and the r is dx dy. Okay, this is dot product. The same dot product over here. Now I discover obviously p is y squared. So p is y squared. And q is x squared. This is my vector field. I copy my vector field. Separate here is y squared, comma x squared. Okay. But I know, according to the Green theorem, okay, we can compute this line integral. Okay, in this case, a little bit not countable because we have two lines. So I need to perform the integral from -1 to +1 for this segment, and the 1 to -1 to come back again to the original by the semicircle. So basically, see, I make a decision to compute this line integral, I need to separate in two pieces. However, I know, okay, when it's closed, we can compute it using the double integral in the region R. In the region R is this region R, okay, of the curve of this vector field, dA, something like that. And dA, I put dA, no dx dy, or dy dx, because I don't know, see, I ending in polar, maybe. Sound familiar because it's semicircle, no? Okay, now so first of all, the first thing you should do is compute the curve in this vector field. So I compute the curve. Well, this is easy because it's two-dimensional. So I have partial q with respect to x minus partial p with respect to y. This is p, this is q, no? Okay, because the partial derivative of q with respect to x is 2x. And partial minus p with respect to y is 2y. Okay, perfect. So now the double integral that I need to do is double integral in the region R, and the integrand function is 2x minus 2y dA. Boom. So now is the crucial moment. We are doing using Cartesian, we are using polar. I suppose that polar is better, right? Polar is better because it's semicircle. So now, immediately I change this integral in polar. Okay, either way, the first way is change one of these two. There are no reason to have it. I put outside. It's a common factor. I factor out. I know that in polar x is r cosine theta minus r sine theta. Okay. Step 1, change the integrand function in polar. Step 2, change the differential in polar using the Jacobian r dr d theta. Secondly, or third, set out the limit. No, the limit is easy. The limit is r vary from 0 to 1. So r vary from 0 to 1 because this is the unit circle, and theta vary from 0 to pi, not to pi, because it's a semicircle. 0 to 1.
Could you explain how you got that graph just really quickly?
Okay, of course. Okay. Let me try to do my best. Look, in polar, So my problem is reduce it to the double integral in that region. Remember, in polar, we have the integration is different. The integration look like a piece of pie, like that. Okay, so the magic of the double integral, look. Suppose you integrate first dr, so you travel in this direction. Okay, basically, look, this is my infinitesimal area, dA, and polar. This is a little bit curvy, and this is d theta, and this is no curvy, is a little bit like SDR. When you are doing this, the action for this integral, you extending r to the limit that you know, or you want, or you need, que es from 0, que es the origin, to touch the boundary of the our region, que es el semicircle, que es 1. So in any case, it's constant, 0 to 1, 0 to 1, 0 to 1. And you know, in the second integral, que es theta, you open the pie from 0, remember theta is measured from the x-axis. So it's from 0, is this, 0 theta. Okay, this is pi over 2. And this is pi. Make sense?
So, Professor, you gave us that in the problem, right? The graph?
Yeah.
That's not something you expect us to come up with on our own, right?
Yeah. Let's give it. Let's give it. Don't worry. Okay. Do you see the review package?
Yeah, I see it.
Okay, this is from 0 to 1 in R and from 0 to pi in theta. Okay, let's do it. This is super easy because the limit is a constant and the function is separable. For example, I am doing that way. I put 2 here, integral from 0 to pi. I copy the theta part, case cosine theta minus sine theta. Of course, your multiplication, you factor out r here, cosine theta minus sine theta. And you multiply this r times this r, and you get r squared. So we separate another integral from 0 to 1, r squared dr. Make sense? Okay. Antiderivative cosine is sine. Antiderivative sine is minus cosine, but we have minus in the front, it is a cosine. Evaluating between 0 and pi, and don't forget multiplication by 2. Entonces, bueno, let's do it. Es sine pi plus cosine pi minus sine 0 plus cosine 0. Ok, cool. Entonces es sine pi es 0, cosine pi es negative 1. The answer that part is negative 1. Sine 0 is 0, and cosine 0 is 1. So actually, we have negative 1 minus negative 1, no? It's negative 2. It's negative 2. Don't forget these two. Well, these two in my paper, well, no, I multiply. It's negative 2. This 2 and negative 2 is negative 4. Either way, it's a fact. Entonces let's focus on the second integral. No, the second integral is easy. It's r cubic divided by 3, no? Evaluating between 0 and 1. When you evaluate, it's easy. It's 1/3 minus 0, 1/3. What's the final answer then? The final answer is minus 4 over 3. Boom. Final answer. Using Green theorem. Green theorem is fantastic. Green theorem allows us to convert the complicated line integral in one easy or relatively easy, you know, double integral. Okay. we finished the first page. Let's move on to the second page. This is more complicated. Any questions so far? Green teorema, no problema.
Yes, no problem.
Okay. Let's do a number 8. Number 8. Again, we have green. No? Yeah, we have green. Suppose que it's important in the test, the green theorem. Okay. Number 8 questions. And you smell this could be possible apply when you see that this integral is a closed curve. Entonces es weird, es xy paréntesis dx plus dy. Wow, I don't understand very well what's that. And the curve is given. It's given. In this case is mierda. In this case is a full circle, unicircle full. Okay. Negative 1, 1, 1, 1. And this is in the counter-clockwise direction. This is my C curve. This C is this. Okay. Well, entonces now some book and study guide and the back of the problem sometimes write the line integral in different weird weight. However, I like you write like that. You apply distributive property. Entonces xy dx plus xy dy. Okay, entonces much better, no? To see who is the vector field associated with this. So the problem clear, do no specification vector field, but you try to find the vector field. Can generate somehow when another guy is doing the dot product, the integral, the line integral gets given, ¿no? I need to solve it. Entonces es obvio que the vector field es xy, xy. So PQ is a P and it's a Q. They are twin brothers. Exactly the same. PQ. Now, if you want, okay, I suppose that you want to convert this problem in double integral in the region R, then you have to compute the curve of this vector field. But it's easy because it's two-dimensional. There's qx minus py. Entonces the partial derivative q with respect to xy minus the partial derivative p with respect to y is x. And the curve is y minus x. No zero. No conservative field. Si es conservative, the answer of this problem is 0. Okay? By the way, it's curiosity. In this example, the answer is 0. However, the vector field is not conservative because the curve is not 0. So now, for sure, I guarantee you 100%. If the vector field is conservative, the line integral in the closed curve is 0. The converse idea not necessarily is true. So some example like this, the line integral is in the closed curve is 0. However, the vector field is not conservative. Okay. 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 Entonces now, let's continue. Entonces my green theorem allow me convert this line integral in double integral. In the region R, you know who is the region R, and the interior part of the full circle. And the integrand function is this, y minus x. Yeah, boom, that's it. Okay, so now we are doing this problem exactly the same we are doing in the chapter 3 when you don't know line integral and you know very well double integral. Okay, so you forgot the magic of the green or the theorem in vector calculus is que you convert the vector calculus problem, maybe line integral, surface integral, and another easy integral, que is not vectorial, it's a scalar, because the function y minus x is a scalar function. And in this moment, you make a decision to apply polar. Why not? Because it's a circle, it's obvious, no? The idea is clear. When you apply the polar, the limit is a constant. We can separate the integral and you compute in easy way. So you are doing by Cartesian, circle in Cartesian is horrible, no good, okay? Okay, so now to do in polar, you double integral, and y is r sine theta, x is r cosine theta, now the Jacobian, que is r dr d theta. And the limit, well, the limit again is from 0 to 1. Remember, this is a unit circle, 0 to 1 r, but in this case, theta go from 0 to pi because it's a full circle. Okay. Okay, one more time, similar to the other example, you factor out r, multiply by r, we have r squared, and separate the integral into integral. So you convert the problem, look, you convert the problem at the beginning, line integral to double integral. Apply polar, you convert the double integral into single integral of the calculus 1. And you compare it separately and multiplication. Done. So 0 to 2 pi of the expression que is sine theta minus cosine theta d theta. Multiplication from 0 to 1 and r factor, common factor, multiplication by other r is r squared dr. It's doing. Well, this is super easy. Wow, super easy. This is the antiderivative r cubic divided by 3. Evaluating between 0 and 1 is 1/3. And compute this. Sometimes happen when you have combination sine and cosine and you integration in one period, the answer is 0. But okay, suppose you don't know, no problem. Antiderivative sine is minus cosine. Antiderivative cosine is sine. Evaluate in between 0 and 2 pi. Plugging in. Teorema fundamental del cálculo. You evaluate here, minus cosine 2 pi, minus sine 2 pi, minus cosine 0, minus sine 0. Cosine 2 pi is 1, but we have negative here, negative 1. This is 0. This is negative 1 again, no? Yeah. Cosine 0 is 1, but you have negative in the front, no? And this is 0. So we have negative 1. And we have how many negative, positive. Is 0. And 0 times 1/3 is 0. Entonces the idea is, in this case we have a vector field. Okay, the vector field, so normally the law is, you see, the vector field is conservative automatically the integral in the closed curve is 0. However, in this problem, happen different. The integral in the closed curve is 0. However, it's not conservative. The converse idea not necessarily true. Everyone follow me? Follow me or no?
So it's not conservative?
Uh-huh. Do you see how do you know it's not conservative? Look at that.
Because the curl equals y minus x.
Exactly. The curl is not 0.
So it's just coincidence?
Not exactly. The problem is that the fact is true is if it's conservative, the line integral and the closed trajectory is 0. This is the fact. The other is pure coincidence. Yes, it's a coincidence. The converse idea es coincidencia que sea. O sea, the majority of the scenario, I suppose que no. Si it's not conservative, of course, the circulation or the line integral and the close is not 0. So the majority, you are at 99% is F is not conservative. The integral in the closed trajectory is not 0. And they are 99% of the case. However, they are 1%. I say 99, but to say one number. The majority. Clear?
Clear.
Okay, erase. Okay. Now, number 9. So I propose you to do only to number 9 today, because the rest 10, 11, 12, 13, and 14 is more complicated and long. Oh, no, okay. To maybe 9 and 10, and that's it. The Stuck and divergence theorem is complicated, and we are doing it in both ways to verify. So doing 9 and 10 maybe today. Okay. Okay. What about the 9? The 9 is again green. No, green. Yeah, green. Using green theorem to find the area enclosed. Oh, area enclosed. So I need to remember the formula. So I is given one vector value function que represent one curve in 2D. This is not super important to see what kind of curve it is. Just in case I did in GeoGebra, you can use in GeoGebra or in Desmos. You know how, right? Remember, you put a curve, this command, you put the x component get cosine square, you put the y component get sine, cosine, sine, you put the parameter t, and your specification of the domain. Remember, okay, you write this, you don't say anything. You need a specification domain, get t, and between 0 and pi. This is given completely. Entonces, si you try to see in GeoGebra, you copy, you open GeoGebra, you put the curve command, you put the x component, get this. You put the y component, get this. No C component, si es C component, entonces the curve es en 3D, pero es one dimension object, ¿no? You set the specification the parameter que es t, and your specification the domain, que es 0 and pi. Boom. And when you are doing this, you see in two-dimension plane a curve like that. It's a circle, a full circle. But the center, no, in the origin, the center is located here in 1/2, 0. Okay, and this is T, for example, let's verification. This is the job of GeoGebra, no? GeoGebra. Suppose that you have no GeoGebra. Well, you can do by hand, you can. Little bit, no? Suppose at T equals 0, you evaluate at T equals 0. At T equals 0, the X component cosine 0 is 1 squared is 1. And Y es cosine 0 que es 1, pero sine 0 es 0. Entonces, this is the point, 1, 0. Do you see? And you can generate point by point. I encourage you, you try pi over 2, que es here. Pi over 4, sorry. Pi over 4. Pi over 2, no. Pi over 4 is this point. Pi over 2 is this. 3 pi over 4 here. And we come back here to pi. The cycle, the period is pi, not 2 pi. So move in that direction. This is the orientation for this parameterization. Okay, cool. However, the job you should do is compute the area of this. The area using geometry is super easy, no? After we try using geometry and verification, because it's a circle. Yeah, you know very well the formula for the area. Entonces now, if you want to find using what is the idea of the problem? Using green. Using green. Okay. And green allow me to compute the area of any closed figure using that formula. 1/2 integral in the closed curve C of the x dy minus y dx. It's a formula. That formula I prove in class. You have a notebook in your notebook. And we're using, when you want to compute the area in one closed curve inside, bounded by the closed curve. Okay, but fortunately, you have the parameterization of this, so I know very well. Okay, x is cosine squared t, and y is cosine t multiplication sine t. Okay, now they define dx and dy is super easy. Just differentiate derivative of this. And be careful, because when you apply the chain rule, you remember the outermost function is a composite function, it's a power, get 2. Entonces you subtracting 1 and put it 2. So 2 cosine t, and derivative cosine is minus sine t dt. And you express it, don't forget dt, because we are working with differential dx, ending dt, something dt. So the idea is clear. Now, likewise, dy, you apply the product rule, because of the multiplication to function, no? This is a function f, this is a function g, and the product rule say, derivative of the first, que derivative cosine is minus sine. Multiplication by the second, without derivative, no derivative, plus derivative the second, derivative sine is cosine, multiplication by f, que es cosine, it's a coincidence, dt, don't forget dt. Entonces, actually, if you want, rewrite this This is a cosine positive, cosine square t minus sine square t. Unfortunately, we have no identity. We have identity when it's cosine square plus, but when it's minus, no. Okay, no problem. Leave it like that. Okay, entonces the parametrization allow me convert this line integral and the single integral of the kind one. Is 1/2 integral. Integral from the domain of t, que is from 0 to pi. Look at that. Okay, my integral, this is from 0 to pi. 0 to pi. Cool. So I'll copy. Who is x? X is cosine square t. I copy cosine square t. Multiplication by dy. And who is dy? dy is cosine square t again, minus sine square t dt. Okay, this is that part. Minus. The second part is y. Okay, y is cosine t times sine t multiplication by dx, and dx is this. Is minus 2 cosine or whatever, cosine t sine t dt. I put double dt, it's okay, only one either way. And you now multiplication. This is algebra. Let me try to do the algebra. The algebra is this time this is cosine 4 power, no? T minus cosine square t times sine square t plus y plus, because we have double minus plus 2 cosine square t, because we have 2 cosine, look at that, and sine square t. Okay, when I have a complicated expression, I copy separately without integral, without 1/2. No, I manipulate algebraically this. Okay, so this is I combine lighter, no? I combine lighter. Who's light? This and this is light. So basically is cosine to the 4 power t plus cosine square t sine square t. Cool. Now why not factorization? At least one cosine square. So we have cosine square t factor out. We have cosine square t plus sine square t. You know very well this famous trigonometry identity get one. And the answer after the manipulation is cosine square t. Wow, amazing. This long problem, long, I simplification like that, 1/2 integral from 0 to pi of cosine square t. Cool. Now the rest is super easy, because one more time we're using half angle formula. You remember the trigonometry, right? It's classical problem in Calc 2. This is 1 plus because it's cosine. Cosine double angle, que is 2t, divided by 2. Double angle. Then now replace. This is 1/2 integral from 0 to pi. And there's a 1 plus cosine 2t over 2. And these two together, dt, don't forget dt, is 1 over 4 integral from 0 to pi of 1 plus cosine 2t dt. Okay, we almost finished. Now, I like separate this into because 1/4 integral from 0 to pi of dt is easy, plus integral from 0 to pi of cosine 2t dt, separately, yeah. I smell que that part is 0 because the same idea, no, is the integral in one period. In this case, not exactly one period, but it is to see it's one period because the period is 2 pi over 2 f pi. You see the period. Okay, one shortcut to simplify your calculus is when you integration sine cosine in one period, the answer is 0 because you know very well that that function is oscillating. No? One area is positive, one area is negative, and one period. Entonces the period of this cosine is period formula is 2 pi over b. Now who is b? B is coefficient here, gets 2. And the period pi is exactly the period que you are integration. Entonces, de ese confirmation que es 0. However, suppose que you don't know, no problema. Entonces, you integration this. Okay, let me integrate this first. This is super easy. Es t, equivalent to 0 pi, es pi. This is pi. I multiply by 1/4, 1/4 pi. Okay, now let me try to prove that this is 0. According to my intuition, they say que one period, something. Entonces, antiderivative cosine sine 2t. Don't forget divided by 2 because this is a coefficient. Okay, evaluating between 0 and pi. So 1/2 again. Sine pi, sine 2 pi. You already have 2 pi minus sine 0. Both are 0. The answer is big 0. And this is the final answer. Makes sense. This answer, according to the geometry, is elementary. You say, no, too complicated. But suppose that you don't know, or you in the moment you are doing this problem, you don't apply algebra to see, because you don't need the curve, at least the shape of the curve. You don't know this is a circle. The radio is obvious. The radio is obvious que 1/2, no? A ver, let me see. Yeah, 1/2. 1/2 is the radio, no? And the radio is 1/2. Entonces I know that the area of the circle is pi, radius square, no? And pi, and radius square 1/2 square is 1/4. Pi over 4. We get the same answer without doing anything. The beauty is that this is general, no? Suppose another trajectory que no necessarily circle, something like that. Well, we can find the area using that formula. In the lecture I did using the elixir, I remember, right? Different every figure. So you parameterize and you apply the formula, you compare the area. Cool?
Professor? It says to use Green's theorem. Is that formula a part of his theorem?
Yeah. Because when I explain the Green theorem, I create some conditions, specific conditions, to find the area. Do you want to get for you now?
Yes, please.
No problem. So the Green theorem originally say que this integral is equal to this, double integral. Of course, this is closed trajectory. And the curve, but the curve is in 2 dimensions, qx minus py dA. This idea is clear. I copied a little bit different, no? But it's clear, right?
Yeah.
So you want to find the area. Bueno, I appreciate so much that this integrand function could be 1 because we have double integral in the region R of the X area, no? Makes sense, right?
Yeah.
Entonces, one possibility is que QX is 1/2 and PY is minus 1/2, right? Because 1/2 minus 1/2 is 1. It's the only possibility, no, it's the only, no, but it's the most popular option que the mathematicians are taking, okay? And entonces you apply antiderivative because I want to find Q is 1/2 X, no? 1/2 X. And here is P is negative 1/2 Y, no? And so you, it's similar to the anti-gradient, no? You apply the antiderivative with respect to the X and antiderivative with respect to the Y. And we come back to the formula. You see that 1/2 is common factor. You put it here. Well, let's do it. P is negative 1/2 Y dx. And Q is positive 1/2 X dy. Factor out 1/2 and organize in elegant way is X dy minus Y dx. Boom, esa fórmula. To compute area using green theorem. Cool?
Cool.
Que es the formula que I using at the beginning. Let me see, compare si I did well or not. Let me see if I did well or not. Oh yes, x dy minus y dx. X dy minus y dx. Okay? Entonces I propose you stop. Because next is a surface integral. And you know, the surface integral is more complicated. Yes or no?
Yes.
Yeah.
What do you think about? So the problem is, surface integral, there are 3 different ways to compute. Using parametrization, the parametrization surface includes 2 variables, 2 parameters, UV or whatever you want to call, R theta or phi theta, whatever. Depending on the surface, it's either parametrization and spherical, cylindrical, whatever. No? We have this way. We have another way that is explicit and implicit, que es similar. It's similar because explicit, you don't need to do any parametrization. No. You suppose que x is x, y is y, and c is f of x, comma y. Or put together and express it in implicit. Entonces, the formula is similar, very, very similar. I don't know, you practice the way you prefer select. The beauty is, of course, you're doing well, you get the same answer, right? Now, in number 9 problem, they want you compute the surface area, and it's given for you the parametrization of the surface. By the way, looking this, I see que es paraboloide. Yeah, it's a paraboloide. Well, how do you know que es paraboloide? Let me, I don't want to do. I want to just copy number 9. Copy number 9, and I like the idea, I retain next time. So the only information that's given is the vector value function that represent one surface u cosine b, wow, weird, comma u sine b, comma u squared. If you want, you put in GeoGebra. this vector value function, you put surface. And you copy the x component, is u cosine b, comma, and y is u sine b, sine, comma, z is u squared. And specification the domain of u very is important. This idea is with a domain of from 0 to 1 and b from 0 to pi. Making sense because b is the variable inside the trigonometric function, and I suppose que the angle, b is the angle, is a variable between 0 to pi, makes sense. And for example, you declare que the variable u vary from 0 to 1, and the variable b vary from 0 to pi. And when you see in GeoGebra, that graph, you see a surface. Okay, I anticipate que es paraboloid because you know very well when you have sine and cosine, it's because my surface have like a cylindrical symmetry on the sine cosine, because you are familiar with the circle parametrization of cosine and sine. Are you familiar with this? No? But of course, the surface and noise is not constant radius and not constant. Suppose cylinder is constant too. In this case, not constant. It's a variable. Okay, the variable vary from 0 to 1. So actually, this radius 1. The z vary pero quadratic and give me information que es paraboloid. Make sense or no? Make sense or no?
Yeah, make sense.
Now the goal que they want is compute surface area. Therefore, you need to convert my problem in one surface integral like that. Surface integral. This is my integrand function. And here is ds. This is capital. Yes. Because this is infinitesimal surface, right? And what about, see, I want surface area. What about the integrand function? What integrand function you suppose? Because the problem don't give me a vector field. No vector field, no. It's no flux integral, no. It's surface area. So what is the integrand function, guys? Can you assume?
1.
Excellent, 1. You understand very well the idea of the magic 1? The magic 1 que converting double integral to triple integral. Okay, you compare the volume using triple integral, or you compare the area using double integral, not necessarily mass, because we are supposed que it's constant, it's equal 1. Entonces, no, it's exactly, the meaning is the same, but the numerical value is the same. It's area, or it's volume. So now, si you assume que the integrand function of 1 is scalar, nice. I suppose que the density of this surface look like paraboloid, no? Pero es no solid paraboloid, es surface. It's the peel of the paraboloid, right? We have empty space here. Basically, my goal is compute this around, of course, surface area. How many material we need to build this paraboloid? Okay, now you suppose que the density is 1, is constant, entonces you compare the surface. Cool? Entonces stop here. I want to send right now, so right now no, but in a few minutes, the video of this plus the new version of the test in Word. Okay?
Professor, maybe can you show it here before you stop the recording, just in case it doesn't go through?
Say again?
Like, could you show, do you have like the online version of it that you have like on the Word document? So you could just show it on here on the recording?
Yeah, absolutely. Yes, I sent. Okay? I understand your question, mister, or no? I sent. I will send. Future, will send. Okay? Okay.
Oh, okay.
That's it. Bye-bye, guys. I have another class.
Bye, Professor. Bye, Professor. Have a nice day.
What do you say?
Have a nice day.
You do.